Okay, so this sort of second session it's about looking at what the PowerVR framework is, why we're using it, and those types of things. Okay, so essentially, yeah, just looking at why we're using it. We're also going to be looking at how can we, so the lab work that you'll be doing after this, the practical work, is very much alongside this session. So you've been given some practical code, but it's all in one class. Okay, so to be able to understand the bits of the graphics commands, okay, we're not looking at shader code just yet, but the graphics commands that you need to display a triangle, for instance, we're actually I'm going to get you to create your own triangle class, move the appropriate commands and things from the main application into that triangle. So the main reason for this is so that you can understand at least what bits of the OpenGLES commands need to be in each class that you want to render something and that type of thing. Okay, and obviously we're actually starting to come to grips with and I'm saying about the commands. Okay, so the terminology here is when I'm talking about the commands, I'm talking about how do we send commands from the CPU to the GPU. Later on in the full module, you then start writing your own shader code, okay, which is different. That lives directly on the GPU. You're overriding parts of the GPU. So the commands are the things that we're calling every frame. We're telling the GPU, okay, maybe draw this triangle, put it there, and that type of thing, okay. So yeah, the contents of this session, so it's looking at the basics of PowerVR, how do we use it, and then just, well, okay, how do we, break that up to use some simple OO design. So the basics of PowerVR framework, it's cross-platform. Now I've mentioned this before, okay, but it does emulate the OpenGLES environments. So this is really, really nice. So it means you can use a PC, you can develop on that. Now, yes, it's an emulator, not a simulator. So if your final goal is to develop to a mobile device or an embedded system or something, then you are going to need to try it on there. But it will at least emulate what's going on. Okay, the performance are going to be different, but it does emulate what's going on for you. So it's, in my experience, much more rapid development to develop on a PC, and then to start to do tests and things on an actual device. So it's really, really nice. And essentially, for each of the platforms, whether it's Linux or Chromebook or BeagleBone Black and so on, there's a different PVR version for that platform. So your code basically sits on top of that. So the way that it works, so we've got this PVR shell, okay, and that is communicating with the operating system, and our application basically talks to this PVR shell. So it's kind of a wrapper sort of thing. So yeah, what this means is we can replace this PVR shell with whatever version we need for the current operating system, and our application remains pretty much untouched. You need to recompile it, but that's it, So it's really, really nice. So just some features of PVR shell is it will create a window for you, okay, and the graphics API context. So you don't have to worry about creating all those things. You can concentrate your time on making your your graphics code and game or whatever you're developing. Say it's very much abstracted, so it moves itself away from whatever the actual OS is. And it does allow you to write C++ and OpenGL ES code on one platform, for instance like a PC, and you just move it across to your other one, recompile it, and it works. Okay. It is C++. Yes. I think you missed the beginning. Yeah, absolutely. So the framework is C++. So what I did say about this is, if you're, are you academic?
Golang, I'm currently finishing up learning.
Okay, yeah. You do need some C++ experience, but what the module does do is it assumes little to no previous graphics experience. So, yeah, okay. So the PVR shell has 5 main virtual functions that you can override, okay, and utilize. I'll look at each of these now, but basically there's a way ultimately the framework will tell you when the application has started. It will also tell you when the application is about to go away. It will tell you when a valid graphics context is being created, and I will cover these different ones. It will tell you when the graphics context is about to go away, and probably the most important one, render frame. That's the one that's called every frame. That's where your graphics code goes in, so you can see stuff. Okay. So yeah, the Init application. So this is where you would potentially want to create and put any general C++ initialization code in. Okay. Excuse me. Now this is you don't necessarily have a graphics context at this point. What that means is, if you were to send graphics commands and things to the GPU in this function, the GPU probably won't even get them, okay? So this is very much about your general sort of C++ things. If you want to create a data structure, maybe an std vector or something, fine. Whack it in here. That's absolutely fine, okay? Any graphics code, probably won't have any effect if they're in here. This just gets called once when the application basically sort of starts up. So the init view, this is called when the context gets created, in fact, changes, I believe. So this is telling you that you have the CPU can now talk directly to the GPU. Okay. So this is where you might want to load in textures. That's the images that we apply to triangles. You might want to create your Vertex buffers. You'll be looking at those very shortly, and so on. So this is where your initialization code, if you want to set up depth testing, or if you want hidden surface removal, that's just, if a triangle's facing away from me, don't draw it. Okay, it's just optimizations like that. All those sort of things can go in init view. And I say the render frame, this is the thing that's going to be called over and over again. Okay, so this is our sort of main loop sort of thing being called. So all your, ultimately everything needs to be in there. All your drawing calls and things like that. So C++, if you've created anything within the init view, then the release view is a very good place to release those resources. Okay, so if you've created a buffer, we should be releasing that buffer. Hence, what we don't want to be doing is chewing up, leaving the memory on the GPU. And so if we've created memory on the GPU, we want to be getting rid of it. Likewise, with the quit application, if you've created any memory on the heap or something, you want to be getting rid of that appropriately. Although my students never seem to do that. But anyway, another thing. So, using it. Now, it's really straightforward, okay? There are two basic steps. One, you just inherit from PowerVR shell. And the other one is to have appropriate header files for the platform that you use. But in the code I've given you, all of it actually just uses a single, includes a single header. And in that, you've got lots of if, def things. So it looks for the OS you're at and it brings in the appropriate stuff. So even that, you don't need to change it if you're moving it onto a different device. So essentially, your application inherits from the PowerVR shell. Okay, just like we're doing that. And the other thing you do need to do, and you'll see this in the code, is you also need a function called new demo. And ultimately the framework, I believe, looks for this so it knows which application to create. So that's it. Okay, you will need to include the appropriate headers, and I've got this header file there, which has all the stuff in it to bring in what's necessary for each different platform and so on. Now, those two very simple steps are great. Now, unless you override the 5 virtual functions, you're not going to see anything, okay? But essentially, once you've done those things, implement the 5 virtual functions: init application, init view, the render frame, release view, and quit application. I'd say at very least you need the init view and render frame, so you can set it, you can load in things like textures, and you can render stuff. But we should be cleaning up things as well. So I say the lab that the practical session you're going to start when I shut up is for you to create a very simple OO thing. So the example code that you're going to start with renders a really exciting yellow triangle on a blue background. Okay. Now, purposely, all of the practical work is just using a single, or maybe a few triangles and so on, but it's just using triangles. Nice looking meshes, that's an artist's job, okay? What we're concentrating on in this whole module is being a graphics programmer, okay? You make that triangle look the best it possibly can, all right? You can replace that triangle with any elaborate mesh, that's fine. What I don't want as an introduction to mobile graphics is to confuse things. So we're not even loading in the triangle, we've got the definition in there so you can see it. It's humanly readable. Okay, so don't want to obfuscate things away by loading in big meshes and nobody understanding what's going on. So purposely left it just to very simple primitives. Right? You can load in a big fancy mesh and apply your thing to it. Absolutely fine, dead easy. And the PowerVR framework will load in a mesh for you, for instance. But purposely left it as triangles because, you know, creating those assets, those meshes, that's an artist's job, that's fine. What I care about is understanding how to do the graphics programming, yeah. How to apply a texture to that image, how to apply lighting to it. Maybe I want reflection and refraction from this triangle, okay. So currently, we've got this single application. In fact, it's a single class. Okay. Now, what we do is we define and set up the shaders. And again, you know, we'll be looking at the shader code. Okay. But much later on in the module, we go into details in what it all is and so on. And ultimately, I say the shaders is the code that allows us to manipulate the triangle, i.e. where is it going to go in our environment and how does it look like, okay? How do we calculate the color for each of the pixels that triangle is on the screen? We're also setting up the triangle directly in the code in a VBO, okay? So a vertex buffer object, I've already mentioned, this is a buffer that lives directly in the memory of the GPU. So it's where the GPU can get hold of it very quickly, okay? And it wants to be able to render the triangle as well. So that's what it's currently doing. We're using a very simple vertex and fragment shaders, and I'll show you it in a second. Okay. It looks like C. Okay, when you actually see the actual shader code. And what we need to do, we actually define inside the init view. Remember, the init view, that's when we've got a valid graphics context. So it means we can pass things to the GPU, we can create things on the GPU, we can talk to the GPU. Okay. Yeah. Okay. So here's the shader code. Okay. So we've got this vertex shader and fragment shader. In the session after lunch, we will actually be looking at the pipeline, how all these sort of fit together. But essentially, the vertex shader works on every vertex on all of your meshes, right? We have a triangle. What that means is we've got 3 vertices. Each corner of the triangle is a vertex, okay? Each one of those vertices will be passed into and run on the vertex shader. Okay. So what this one's doing, this again further on in the course, all of these are more explicitly done. But the attribute, that's a property, if you like, of the vertex being passed in. We at very least need the position, and that's what this my vertex is. It's actually the position of the vertex. Now you can have lots of different attributes for each vertex. So a vertex could have, you have to have a position, otherwise you can't move it somewhere, you can't render it on the screen. But you might also have the color for that vertex. You might have the texture coordinate. So if you want to apply an image to it, and the practical session in this afternoon, you will be looking at texture coordinates and things. Which part of the image should be applied at this vertex. A normal, for instance, so a normal is telling the GPU which direction that vertex is pointing in, and so on. Okay, so there's lots of attributes that you can pass in for each vertex. Okay, so each of these properties, these attributes, as it's called in the shader code, it pertains to that single vertex. Now, because of the architectures of modern GPUs, you have the very, very highly concurrent. Okay, so the GPU in my office has 6,000 CUDA cores. Okay, it's just those hugely, bonkers numbers of. So what that can do is it can process. But what it means is this vertex shader the same one can be run in parallel on lots of different vertices all at the same time. And that's why GPUs, are very much really, really scalable, okay? Because they're all independent. So each vertex will come in with its attribute. You at least need the position. What you can also do in the vertex shader is you can calculate and create a normal or a texture coordinate or the color or any of those things, but you must pass in the position of it, okay? This is the model view projection matrix. We talk about this sort of later on. We'll be looking at transformations, but essentially this is a 4x4 matrix that describes how each vertex should be manipulated in the world. So should it be rotated? Should it be translated? Should it be kind of scaled? What type of camera do we have? What's the field of view? That's all encoded in a single 4x4 matrix. Okay, so that wants to be passed in, and then very simply in this this is as simple as it gets, folks, is all we do is multiply the position, this is a vector, by the matrix, and that gives us the position of that vertex in our environment. Okay? So this is as simple as a vertex shader goes. Now out the vertex shader, it goes through the rest of the pipeline and eventually ends up in the fragment shader. So the position for each of the vertices is calculated. The fragment, so that's basically saying that the rasterization happens, I'll be talking about this later, but ultimately all your triangles are projected onto your screen, and the bits that needs to be colored in comes into this fragment shader. Now here, I'm just choosing, this is just red, green, blue, alpha. Okay, we're not having any transparency here. So red, green, blue, as you can see, it's kind of a mustardy yellow color. 0 would be none, 1 is full. So full red, full green, and 2/3 blue gives you sort of a musty sort of color thing, okay? And that's the color for this particular pixel. So that is as simple as it gets. And say throughout the full teaching material, we'll be going through these extensively, adding lots of things and so on. And notice that it is OpenGLES 2.0 compatible, this. The other thing that you'll notice is that you've got these uniforms. So this matrix, we want the same matrix to be applied to all vertices, because that matrix, or all the vertices coming in for this particular mesh and so on, because they're the same. So that's why it's uniform, because it's uniform for all the vertices within the current mesh that we're using. The attribute is going to be different for each vertex coming in. Cool. Yeah, so why? I say one of the reasons I want you to do this is to understand which bits of the graphics commands you need to be able to call and set and use for each of your different sort of meshes and things like that. Okay. But also, if we had every single bit of graphics code in one massive class, it's going to be unwieldy. Okay, you cannot develop, a full game or graphics application like that. Okay, so we do need to be able to think, well, okay, if we've got this triangle, let's actually have a triangle class, and that's what you're going to be doing in a very short while. Okay, so essentially, the application class, or I can't remember what the class I've actually called, but ultimately this application inherits from PVR shell, so that's good. This application will have our 5 virtual sort of functions in there. You can create any number of instances of triangle. Okay, so if I want to display 3 triangles on the screen, then I can just create 3 instances of triangle, and I can initialize the triangle in a particular position, and I can tell the triangle to render itself. Okay, so it's very basic. We've got in the triangle class, I would have some initialization method. In here, we can set up our vertex buffer object. So we will be looking at that, but ultimately this is just describing our triangle, and it will live directly on the GPU. And then some way of rendering it, because remember the render frame virtual function that will be in here that we've overridden needs to send all the graphic stuff. So within that, we'll just call the render method of each of our triangles so it can render itself. Now, ideally, and in fact in the second lab, you will be doing this. I'm actually leaving the shader setup in the main class rather than the triangle at the moment. So the purpose of this is to learn about some of the migration, okay? And in the second part, you'll actually start with the shader code actually in the class. It's the triangle class and so on. Okay. So vertex buffer objects. So this is describing our meshes. Okay. So here it's just a simple triangle. Okay. So we're going to include the position of each of the vertices. Okay. So it's X, Y, Z coordinate in our virtual space. But you can also include things like texture coordinates, colors, normals, all sorts of things. Okay. And I've already mentioned it actually lives directly in the graphics memory, so it's really fast for it to access. So in terms of what the triangle class could look like, so looking at the header file, for instance, we do need to include this EGL context because that ultimately is everything that we need for the current platform is in there. Two sort of properties. One is a handle to the VBO that will be created. What is nice about OpenGL is pretty much everything you create using OpenGL, the handle is just an integer, okay, an unsigned integer, okay. And it'll be a positive number, so it'll be 1 or 2 or 3 and so on. Okay, so that the handles are really, really simple. It's just an integer you get. Okay, so we need a variable so we can say, okay, we want to use this VBO now. As I say, it's just a single number. Okay, just a 32-bit integer. We also want to be able to know where our triangle lives in the environment. So I've got X, Y, Z. Okay, very simple. Constructor, destructor, and then here I've got my init. Well, in here I'm going to initialize the VBO and things like that. Render, well, I want to be able to render myself. And I also want to be able to set this position. Yeah, you could put it in the constructor, of course you could, but I've chosen just to have this set position so I can change its position in my sort of application. Yeah. So all I'm going to do is set these X, Y, Z to these X, Y, Z parameters coming in. So when you do that, if I've got this triangle class, then I can create multiple instances of triangle, give them a different position, and get them to render themselves. Okay. Good. So essentially, in the application class, we can create as many instances of the triangle as we want. Now again, just for simplicity, I'm not using an STD vector or anything like that. Just creating on the stack, very simple, just 3 triangles. Now at the appropriate place, I'm going to set the position of each of my 3 triangles. Okay, one to the bottom left, one in the sort of in the middle towards the top, and one on the bottom right. Now, in OpenGL, you've got your X coordinates going across, okay, positive going to the right. The Y is going up and down, positive is up, and the Z coordinate is basically the in and out of the screen. Positive is towards you, negative is away from you. Okay, so if you want a triangle to go into the screen, you need to give it a negative sort of Z type thing. Okay, positive, it will move towards you. Once we've set the positions, we can initialize it. Again, just to keep things simple, the vertex buffer object actually uses the position information to create the VBO, okay, the vertex buffer object. So you do need to set the position before we initialize it. But then in the render frame, we can just call render on triangle 1 and on 2 and on 3, and it appears. Okay. So if you can see, we're kind of doing the same thing each time. So eventually, we'll actually be looking at things like, put it into, I don't know, an array, or probably better, a vector, C++ vector, STD vector. where we just put them all in there. We just call init on each one of those things and then render on each one of those things and so on. So in the triangle, in the initialization method, what we need to do is to create our VBO. Now I'm going to go through each of these now. Okay, it is also described in the lab tutorial as well. Okay, so essentially we're creating the positions for each of the vertices. Now this is a triangle, so we've got 3 vertices. Okay, we've got 3 corners. Each of them has X, Y, Z, X, Y, Z, X, Y, Z. So there's 9 floats here. So these first 3 are describing the bottom left corner of the triangle. The next 3 are the bottom right vertex of the triangle. And the last 3, X, Y, Z, is describing the middle top vertex. Okay, so those are the positions. So essentially, that's what we're doing. So just to make it a bit simpler for you, this is going directly onto the GPU memory. Okay, so we've got the first vertex, second vertex, third vertex. Okay, so just to illustrate what's going on, the first vertex is this bottom left. We're putting it at, I've just not included the z equals 0 because they're all at z equals 0. Okay. So I've just ignored that bit just for simplicity. So this is the first vertex down here, second vertex, third vertex. If you noticed, I'm actually defining my triangle in an anti-clockwise direction. That's on purpose. Does anybody know why? Essentially, yeah. So it's to do with hidden surface removal, right? So I mentioned that, and again, in the full course, we go over this, but ultimately, some optimizations are, if we assume that none of our objects, our meshes, are just single triangles, okay, there's, you know, if you've got a sphere, for instance, and you never go inside that sphere, then we only ever see the sphere from the outside. So what we don't want to be doing is rendering a triangle that's facing away from us. That's just pointless. It's wasteful. Okay, so better to basically cull that. So with this sort of hidden surface removal sort of switched on, okay, what OpenGL does, it doesn't, even if you apply a normal to this and say they're facing this direction, it doesn't use that. It uses the direction that these are created in. So if you create this triangle in an anti-clockwise direction, as I've done, the front face of that triangle is facing us. If I did it in a clockwise manner, the front face would actually be facing away from us. Okay, so when you switch on hidden surface removal, and if you do that and suddenly half your triangles disappear, it's because you've probably defined some of them in the wrong aspect. Okay, so it's just worth mentioning at this point. I have defined these in an anti-clockwise manner on purpose. Okay, because I want the triangle to be facing us. Okay, it's more of an aside. We'll cover that much later on. Okay, so the next one is a line of code in the init is this gen buffers. What we're doing is we're generating a single vertex buffer object. We give it the reference because this function actually creates the VBO and it populates our variable with a number. Okay, so if this is the first one, it will be 1 in this sense. Now you can, if you've got an array, you want to create, say, 10. If you've got an array of 10 integers, you can say I want 10 and it will create 10 buffers for you. Okay. The next line of code is to basically say we want to use that vertex buffer object. Remember, OpenGL, okay, and OpenGL ES, everything's done sequentially, okay? So anytime you want to do something with a particular vertex buffer object, and you can have as many vertex buffer objects as you want to, providing you've got enough memory, This is basically switching on, telling OpenGL, actually, the GPU, we want to use that VBO now, please. Okay, so this is kind of a set thing. Okay, we're binding. You also bind textures and things like that. Basically, it's just the terminology. It means we want to use that VBO now, please. Okay. So the target, this is an array buffer. Okay, because that's what we've created. This is a VBO, basically, sort of thing. This is basically an array of all our numbers. But you can set it to lots of different things as well. Now we've set the buffer, and we need to send our 9 floats, our XYZ, 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 across to the GPU to be stored in the VBO we've just said we want to use. So we use this buffer data, okay, we set the target, well, it's just an array buffer. How many bytes are we sending? What are we sending? Okay, so that's what we created here. This is the data, okay? So what are we sending, and how is it going to be used? So in this example, it's an array buffer, because that's what we're using. We've got 3 vertices for each triangle. We've set them as floats, so for basically each vertex, we've got 3 floats, and it's a triangle, so we've got 3 vertices, okay? So I've just left it like this. So that's how many things are in there in bytes. There's the data, and static draw just means we're not going to change it, okay? This VBO can be static. We're not changing any of the information in there at any point. And then finally, you don't, strictly speaking, need to do this, okay? But this bind buffer 0 basically just says, right, we've kind of finished. We're kind of unbinding. Now, in theory, you don't need to do that, providing that everywhere else in your code, you make sure that you bind the right VBO when you want to use it and stuff like that. I just like to kind of switch it off just so that you don't, so any bugs should appear a lot sooner. And then finally, we just need to figure out how do we render it. Okay, so this is what you need in your triangle class. So the first line is to say we want to use that VBO that we've created. We need to basically sort of switch on in our shader code, if you remember, we've got this my vertex, which is the positional information directly in the shader code. So what we're going to do here is saying, well, the vertex attribute, which is this thing, is at what position? Because you can have lots of different attributes. Now, in the code, this is just set to 0 because it's the first one. Okay. Essentially, you just need to tell the GPU in the shader code where is the position of the vertex going to be. And it's just, well, there is only one, so it's going to be 0. It's index 0. If you had a second one, it would be index 1, and so on. Again, we cover this in the full module. Then we need to basically set up, well, okay, what is the information being passed in? Well, it's a position. It's at index 0. There are 3 vertices, they're floats. This other thing, this normalized, so we don't want to normalize it. If we normalize the position, then we don't have a position anymore. They'll all be between sort of 0 and 1. So that doesn't make any sense. And then we've got the stride and pointer. Now, we don't care about the stride at the moment, so I'm not really going to mention it too much. In the next session, when we have texture coordinates, we very much need to work out what the stride is and so on. And the last one is just where do we start drawing from? Well, we want to start from the very first one. Okay. And last but no means sort of least is we need to be able to draw that VBO, the information that's in there. So we use draw arrays. There are triangles, which has got the 1 at the moment. And we essentially want to start at the beginning, and there are 3 of them. Okay, there are 3 vertices. And I like to switch it off afterwards. Okay.